So welcome to the Total Control Dissemination Workshop. My name is Gregor Giebel. I'm a head of section at the Grid Integration and Energy Systems section at DTU Wind Energy. And I'm the dissemination work package lead for the Total Control EU project. The Total Control project has been running since 2018. And the head is Gunnar Larsen, who's going to be the one with the first talk of the day. And then we'll have 5 more talks on different of the results that we're showing. As I mentioned, please mute your microphone when you're not talking. Also, it's probably best if you shut off the camera and just let the speaker be on screen. But if you want to have a question in between a short one, I think we have time for that, then just switch on your camera and do it. Or probably better, put your question in the chat. And maybe it's going to be picked up by some of the other participants before we even have the end of it. So with those preliminaries out of the way, it's my pleasure to ask Gunnar Larsen on stage on the virtual screen.
Yeah, I'll try to share my
presentation. I'll stop sharing and Gunnar should be able to share then.
I'll do my best. Let's see here. Can you see my screen?
Yes.
Okay, then I just have to make it a little bit bigger. Like now, is it okay?
Lovely.
You can hear and you can see the screen. So thank you, Gregor, for this nice introduction to this Total Control event. As Gregor pointed out, I'm coordinating this EU project, and I'll try to run through the basic thing, the overall picture of this project, and then later, after me, then we'll go in much more details in each of the 4 work packages. So the outline is as follows. First, I will say a little bit about the consortium, then come to the overall objectives and the approach that we want to use, and then in a little bit more detail on each of the 4 technical work packages, and just end up by showing where you can find information material on the Total Control project, and that relates to work package 5, the dissemination. So about the consortium, you can see we are 8 participants, and these has developed over time. So you can see the names here. It's not the name of the participants nowadays, but well, we have DTU, my organization, then Danish Technical University, and then we have TotalControl University in Leuven. We have Syntef, we have Gerald Hatton and partners and DVNTL. We have Vattenfall, we have Catapult, Siemens, and Statoil, that is now Equinor. So you see we have representatives from the academia, and we also have industrial partners. Some of these are representing expertise in the component production. That's the wind turbine manufacturers, in this case Siemens. We have technology developers, and that's mainly DLV and DL. And then finally, we have 2 end users, that is Vattenfall and Equinor. So much about the consortium. So now we come a little bit into the project activities. So the overall idea with the project is to develop integrated wind power plant and wind turbine control strategies with the aim of maximizing the life cycle profitability of a wind power plant. That's of course the goal for all developers to have a good business case there. And we would like to do that by maximizing the power production, and we have to balance that against the loading of turbine, because it can be costly if the fatigue degrades the turbines faster than necessary, and also operation maintenance, which is quite a significant part of the expenses has to be taken into account. In addition to the operation or optimizing the operation of the wind farm, then we also like to take into account ancillary services. That is some demands coming from the grid operators, and this can also be an issue that is related to the profitability of the wind farm. So an important thing is that we have, of course, a range of models here, but an important thing is that we like to validate these. So for each of these work packages 1 to 3, you will see that we have full-scale experiments, an important part of the project, and for work package 4, which is the closed-loop control activities, we have lab scaling experiments. So in one sentence, the ambition is to move the controller philosophy from greedy individual turbines to wind turbines inside this wind power plant to collaborate and obtain an optimal performance of the wind power plant as such. So this is a very densely populated slide, so I don't want to go through all the details here. I just mentioned that we have these. Can you see my cursor here? I hope so. So we have, as I said, these 4 technical work packages. Work package 1 is about wind power plant design and control models. That's a lot with flow fields modeling. Then for work package 2, we have quasi-static or open loop control. For work package 3, that's a work for an activity dedicated wind turbine control, of course, with the aim to fit into the wind power plant control. And then finally, we have work package 4 with the closed loop control activities. And then, as I already mentioned, you can see here in the green box below that we have a verification and validation effort in each of the work packages. Besides the technical work packages, we have work package 5, which is about dissemination, and finally also work package 6, that is the administration part. So now we come to each of the work packages. Work package 1 is about simulation models and validation of these. So we want to develop and validate a hierarchy of models ranging from high-fidelity models to engineering models. And what you see here is on your right-hand side, that's an example of a CFD-less computation of the entire flow field of a wind farm. And on your left hand is a flow field reconstruction based on full-scale LiDAR measurements. So as I said, the modeling ranged from high-fidelity models via medium-fidelity models to engineering models. And if I go a little bit more into details, for the high-fidelity models, we have CFD-less models. And it's important here to note that there's a dynamic simulations, and we need that if you want to go into loads and not only consider power production. Then we have what I characterize here as medium fidelity models. We have 2 of these. One is dynamic, that's the dynamic wake mandering model. And in this in the context of this project, we have generalized that to account for yacht wind turbines. That's a functionality it didn't have before. And another medium fidelity model is a static model. That's a linearized range model, which is called Fuga. That's a D2 kind of product. And the nice thing about that is that it's super fast, and therefore it works very well with optimization of this kind of problems. Lastly, but not least, but not least, we have simple engineering models, or relatively simply. So we have a dynamic wind farm model based on the DVN-DL Longskin model, where we have engineering wake models embedded in a dynamic flow field, and from CUL we have a static model coupling the Gaussian wake model to background atmospheric boundary layer features. So about the showcases, which is important for validation and working with this model, we have defined a reference wind farm that includes orbit. That's on the upper slides here. You can see the layout of that, and what's done in the project is to investigate consequence of different type of inflow to this wind farm. And we have another important showcase, which is the Lillgrund. That's on the slide, on the pictures below. You can see how it physically appears from this picture from an airplane from Copenhagen Airport. The next picture, the middle one, is trying to illustrate the experiments that we are doing out on the Lillgrund, where we have one lidar scanning forward to define the inflow condition to the wind farm, and two lidars, and that's presented with these curves. They have an area in common where we can reconstruct the wake effective flow field. And one example on this reconstructed flow field is shown in the last slide in the bottom, and I'm sure we'll come back with much more detail on this fantastic experiment. So now we jump to workbench 2, which is about open loop control schemes. So the idea is here to develop and validate optimized wind power plant control schemes, and in the context of workbench 2, we are dealing both with power but also load and electrical aspects. So basically there's two different, at least in this context there's more in reality, but in this project we deal basically with two types of wake mitigation or active wake control, if you like. These are illustrated on this graph below, or this picture. So one is derating, and another one is yaw control, where you deliberately change the position of the downstream wake. So far we have worked mostly on the derating part, but we have prepared our tools to be able to also look into the yaw control way of doing that. So one example is a static approach, where we have the wind power plant production as the objective function, and these optimizations are then performed conditioned on mean wind speed in the inflow, and also wind direction, because that will change the topology as seen from the wind. So what we've done is to derate using two design variables for each and every turbine, and that's the rotation speed of the rotors and the collective pitch of each and every turbine. And what we have been doing is to model these turbines using this linear CFD code that I mentioned in workbench 1, called Fuga, because it's super fast, and it has been done using an actuator disk formulation of the turbines in the wind farm. And we have illustrated that using the Lillgrund as a showcase. So here's one example for a particular mean wind speed, 9 meters per second. And you can see from this small movie that when the wind direction is changing, then the optimal setting of each and every turbine is also changing. So the wake is the blue part, the dark blue, the higher wake, and the turbines is illustrated, or the derating of the turbines is illustrated with the yellow red curves. So the more derated, then of course the more dark, the more dark red it'll be. And it's characteristic that at the end turbines there's no derating, which makes perfectly sense, of course. So another approach worked with in workbench 2 is an attempt to include loading also as a parameter. So there we need a dynamic approach, and the key work there is really surrogate models, and that's obviously due to CPU issues, because that's the way we can do the optimization. Otherwise, the complexity of the flow and the computation will do that. It's not really doable to go through these cases. And what has been shown here is computation of a derated case from the Lillgrund for a particular wind direction 220 degrees. And what has been pictured here is to the left, that's the tower base. The tower base fatigue fatigue loading of the turbine, and on the right, that's the blade root fatigue loading of the turbine. Both of these are based on a surrogate model that has been created using the dynamic wake mentoring model and then a surrogate model approach. So again, here with Workbench 2, we also have full-scale experiments, and that's really a fantastic opportunity that we have got together with the Vattenfall and Siemens, where they offered to derate in the first place a complete row of turbines in Lillgrund, and then compare to cases where we do not have the derating to see the effect of our tools here. And eventually, if everything goes as we are hoping, then we will most likely also try to derate the entire Lillgrund wind farm. And that's that's really a fantastic opportunity in my case, in my opinion. So moving to Workbench 3, that's the enhanced wind turbine control functionalities. So this is just about, as I said, just about wind turbine control, new functionalities there, but of course with an eye of using these for, eventually using these for wind farm control. A very important activity, this activity is a little bit built around a big 7 megawatts Samsung turbine in Scotland, where we use this turbine as a showcase, and we are in the very lucky situation that one of the partners has been really the designer of the control of this turbine. So that's also a unique position to be in, usually for at least the academia. The control algorithms is not that easy to access, or almost always impossible. So this is a very nice showcase, and we look into power set point reduction algorithms and active yaw control, model predictive controller. It's also an activity, and there's some challenges there that has a little bit to do with the CPU power in the turbine, but the principles are in place there also. On top of that, we have individual pitch control and using tower sensors to activate these, and of course LiDARs is to control. So LiDARs is also used for looking into the effect of this wind turbine control, or these wind turbine control functionalities. Right now, speaking, we are about to conclude wake deflection, wake deflection using active yaw. We have a quite comprehensive test matrix that is almost in place now. And what are we doing? You can maybe start by looking on the picture to below to the right, where we have installed 2 LiDARs on this huge turbine. One scanning forward, denoted by 1 here, and another one scanning in the wake affected flow field behind the turbine. A long-range LiDAR, and to the left, you can see the scanning pattern of the Cannot really hear that. Okay, so we have the spinner LiDAR scan pattern here to the left. That's the scanner that records the inflow to the turbine, and then in the middle you can see how we can record and make a flow reconstruction that will show how the wake affected flow field behind the turbine develops. Now finally coming to the closed loop control. So the objective is here really to collect all the developments that have been going on in work packs 1 to 3 to unification of these results into a suite, as I said, of practical wind power plant controllers. And there's also a little activities and guidelines and standards related to that. So some of the things that we aim or we plan to take into account in this open loop approach is to account for model uncertainty and also some variability of external condition that can be based on online input from the turbine and the wind power plant. And here's just a sketch, some of the very recent result. I'm sure that Carl will come into details here. So this is a very comprehensive linear model that describe a wind power plant supervisory controller. So I'm not going into details here, but leave that to Carl. Then finally about dissimulation, I think the easiest thing to say here is to there's of course plans for conferences and journal papers and a lot of other things, but if you go to this website, then there's quite a lot of information about the project. And this is then the end of my introduction to TotalControl.
Thanks a lot, Gunnar. I didn't see any questions in the chat. Do we have any questions now?
Well, otherwise, I'm sure that when Johan and Anand and Ervin and Carl go into the details, then there'll be other options for questions there.
Exactly.
And Elliot, of course. So I will just stop sharing them. Is that okay?
Yep.
Okay, hello everyone. Can you just verify that my microphone and camera are working? And that
it's super.
All fine.
Okay. Well, welcome to everyone that's here and to the YouTube audience in the future. Thank you also to Gunnar for introducing the project and framing what I'm going to speak about here, which is the full-scale measurement campaign, the first of the 2 that we're performing within TotalControl project. And just to quickly say some words about myself, I'm working in the engineering team at DTU Wind Energy in the measurement systems and methods section, and I'm technical lead for performing the LiDAR field campaigns and test campaigns that we do. So one of the most recent projects that we've been working on and still working on is this TotalControl project, and I'm going to walk you through some of the work that we've done. So just to talk a little bit, I know that Gunnar briefly introduced this, but the first of the 2 measurement campaigns occurred here in, it's called Lillgrund Offshore Wind Farm, and it's in Öresund Strait between Denmark here on the left and Sweden on the right. And it's owned by Vattenfall, who is a partner in the project and who contributed a lot of help in getting the installation and also on delivering the operational data that we've been analyzing. So you can see very clearly, and if you ever take the train between these 2 or drive, you can on a clear day see the wind farm. It's quite nice. So just some words about the equipment that we're using to do these measurements. Here's a photo in the bottom right, and it's a scanning LiDAR, a pulsed coherent scanning Doppler LiDAR. And the core idea is that we're simply moving the measurement position using the scan head here in order to position the laser beam, which measures the component of the wind speed that's projected along the beam path. So we have a lot of complexity with this instrument, but we can do a lot of things with it. It's very versatile in that regard. So with this system, we're able to measure up to around 10 kilometers. And given the correct conditions for performing those measurements. And we can also measure at multiple positions along the beam. But there's a couple of additions that DTU has made to this system, and what we call the long-range wind scanner system. And those we've actually leveraged in this project. So the first one is that we can perform complex scan patterns where we can give arbitrary positions, and the scanner will follow those. You're not limited to presets provided by the equipment manufacturer. We can also do multi-LiDAR synchronization where we use multiple of these individual sensors in a combined system to measure multiple components of the wind vector at once. And we can combine these together using a communication protocol we've developed called RSCOM Pro. So in the Lillgrund campaign, we installed 3 of these individual sensors and monitor them collectively and control them collectively. The first one, which was just one sensor, is this middle one here that's placed along the front row of the wind farm facing in the southwest position. And that's measuring the inflow to the wind farm. So we have a reference for example, for doing all the simulation work that you're going to hear from Johan about after my talk. And also just to give an indication as to the conditions, wind speed and direction that's not influenced by the wakes of the wind farm. So we have turbulence, wind direction, wind speed, things like this. And the other 2 are the ones on the left and right. These are the same individual sensor, but they're used together to create a dual Doppler measurement that we actually synchronize the position in time and space along a complex trajectory, which I'm going to present in a second. But just to say, the entire data set comprises of the LiDAR measurements, the inflow and the wake interfarm wake measurements. We also installed some cameras around, or a camera around facing into the wind farm, just to give a montage of the conditions during the tests, which I've made videos into. And we also have the high frequency SCADA from every turbine in the wind farm, and load measurements as well from the turbines that were instrumented with load sensors in the blade, mainly blade root and tower strain gauges. And during the campaign, we've measured, of course, normal operation, but we also demonstrated some of the control concepts that Gunnar has presented. So dynamic wake steering and induction control or power reduction of the leading row of turbines. And we've, of course, collected that data set and are using that for an analysis. So I'm just going to show you here. So I'll just walk you through this. On the right-hand side, we have a plot of all of the wind farm, and the green stars here show where those LiDAR sensors were installed. So as I mentioned, the system we call VARA, measuring inflow, and the 2 systems here, Sterena and Levante, measuring this transect line. So what I marked in black here are the time and space synchronized positions. So when I play this video here, you'll see basically the intersection point between these 2 are following this path at 3 different heights. So we have basically one vertical plane produced that's fully synchronized in space and time, and then we have all of the overlapping area, which is synchronized not in space or time, but can be averaged to create a 10-minute wind field reconstruction. So the inflow is a 60-degree PPI scan or sector scan, and at 8-degree elevation angle, and covering up to 1.5 kilometers, and that's the length of this white line here. Every 30 seconds, we have one sample, one reconstructed UNV component. I'm going to play this video for you, and you'll see the beam positions. This isn't real time because we concluded the campaign, but I recorded it just to show. So you can see, for example, the intersection of these beams moving, and again, it goes between heights. So we have the first height, and then it jumps to the second height, scans back, and then jumps to the third height and scans back again. And you can see here on the left-hand pane, the red and green, which correspond to these 2 systems. You can see when they're basically in the center, you can see the wake That's basically the deviation of this line. And these are just the radial speed measurements. So I'll show you in a second what it looks like when it becomes reconstructed. Yep. So basically, as I just mentioned, the entire overlapping area can actually be reconstructed into a horizontal slice of the wind field at a given height. So here we've chosen the hub height measurement, and you can clearly see, so each frame of this animation is a 10-minute averaged, as I mentioned, because we're not scanning this whole area synchronized. We have to perform an averaging of it. But this test here is actually, let's see if I can get it to play again. Yeah, so it's basically done during one of the yaw test campaigns. So this is a 20-degree yaw test, and we're currently working on extracting the position and deficit and all of this sort of information about where the wake should go, and then to compare that to the modeling results that Gunnar has mentioned. So yeah, that's basically what I wanted to show you. Just a brief overlook about Lillgrund campaign. Right now we're focused mainly on the second full-scale campaign. That's the campaign in Scotland, where we're performing those advanced control concepts that Gunnar has introduced there. And that's going well right now. We have a lot of great data coming from there, and will be available to the partners, and also to, as I understand, we're very open for doing collaborations in this project, and you're very welcome to contact me or to contact Gunnar about how we can go forward with that. So I'm of course happy to take questions if anyone has them about this campaign or about the equipment or the aims of the measurement and test campaigns that we've done here.
Thank you, Elliot. Do we have any questions to that data set? Or to any of the other issues that Elliot brought up? There's nothing in the chat.
You can always write me later on if you need a moment to think about it.
So maybe one can just mention that in Scotland, we are not only looking to yaw deflection using the turbine, the yawing turbine, but also looking into the consequences of derating of the turbine, the consequences on the wake behind the turbine. So yeah.
Yes, and I expect we'll do another webinar probably to present the results of the Scotland campaign. And we already have some good results, but I think we should limit the amount that we present in one short period of time.
Yeah, I also am pretty sure that some of those results here are going to get into the next video, which we should be finishing at the end of the year, but I'm a bit doubtful whether that actually is going to happen, but let's see.
We have a lot of media surrounding the campaigns. It's important to document the operation so we can refer to it later. So as I mentioned, there's wind farm montages, which we're also doing in Scotland on the turbine, and all of the scans and basically animations from those.
And on top of that, we also have quite a lot of SCADA data during the recording of these fields.
Yes, that was a very important thing to have. So
Okay.
I'll hand it over now to Johan, and who's going to present his work, his part of the work, starting from the measurement data sets that we provided.
Exactly. Johan Meyers is a professor at the Catholic University in Leuven. And his specialty is how to simulate all that wind flow in a wind farm. And he's the work package lead of the wind farm simulations work package. Please.
Yes, thank you. Good afternoon. I hope you can all hear me well. So I will talk today about high-fidelity wind farm simulations and data sets. And let me just start right away with showing, a snapshot of a typical output from these simulations. We have done different simulations, but this is actually a wind farm simulation where you see now the velocity field in 3 views. So the top view, the side view, and the front view. And actually this flow field that you see, the inflow that is generated to make this simulation is done in a precursor simulation. That is a simulation that comes in front of this domain. I will also be talking about that. And then each turbine is actually represented with an aeroelastic turbine model. And so there's also loads, etc. monitored. And all this data is publicly available for downloading if you are interested in that. So that's basically what I will be talking about today. So let me acknowledge a number of people here. So this actually been a collaboration between KU Leuven and DTU. So we did a lot of different simulations, and some of them were done in Leuven and some of them were done in DTU. So this is the team of the people that have been involved. I think the one contributing most definitely recently has been Ishan Sood. He has been doing all the wind farm simulations, and Wim Munters has actually been involved in the precursor simulations that we have used before that. And then on the DTU side, it's Søren Andersen and Niels Strohbroek that have done the simulations. Today, I will actually not show simulations from DTU, but they are quite similar to the KU Leuven simulations. And just to keep things easy, I just used basically the simulations that we have at the moment. So this is what I will talk about. I will briefly talk about the TotalControl reference wind farm, because a lot of these simulations are about this reference wind farm. Then I will talk about these precursor simulations. They are very useful in themselves, and I will try to convince you about that and also to show you how you can use them. And then I'll talk briefly about the wind farm simulations and the data accessibility. Okay, so when we started this project, we wanted to do the Lillgrund wind farm, and that's a very important wind farm for us because we have this experiment in Lillgrund. But we also wanted to have a wind farm that is somewhat more to the size of a modern wind farm, so much bigger, larger turbines. And so we also set up some kind of a reference wind farm that resembles what would be a modern wind farm. And so first thing was obviously to look at all kinds of wind farms that exist and reference wind farms that exist. But we concluded very soon that actually the type of wind farms that you find, and even the reference wind farms that you find, they're not really designed with these kind of large set eddy simulations in mind. So we did an exercise where we ended up with this kind of reference wind farm. So you see the white dots. They are spaced in a regular way, as you can see. It's probably not exactly the way it will be done in a big modern wind farm, but this is done intentionally because it gives some symmetries in the simulations. So if you want to do different inflow angles, we don't need to scan 360 degrees, but in this case only 90 degrees, and that reduces significantly the number of simulations that you can do. And what you can also see is that we have chosen a very a long shape in one direction and a shallow shape in the other direction. It is partially related to the fact that we needed to fit our simulation domain around it, and at some point, if your simulation domain becomes very big, your simulations become just infeasible. And the second reason is because by rotating this wind farm, you basically get either a deep array where you have like a lot of wakes interacting, or you have an array that is not so very deep. In this particular picture, the array is clearly not very deep, as you can see. So for reference, you also see the Lillgrund wind farm at the back of it. So these turbines obviously have a much smaller diameter than the DTU 10 megawatt wind turbines that we use in the reference layout. And that's also why they are, much tighter spaced and much closer. Actually, they are very tightly spaced also in terms of their own diameter. In case of Lillgrund, I think you all know that, obviously. So this is actually the reference that we are kind of interested in. And so to do these kind of simulations, so this is actually the simulation box in which we are going to do the wind farm simulation. But at the same time, we are generating turbulence in a similar box that is actually would be placed in front of the wind farm. Okay, and this precursor simulation, as we call it, actually, that just simply uses periodic boundary conditions and generates turbulence in some kind of a self-contained way, and that is what we then use as an inflow to the wind farm simulation. So actually the colorful picture that you see in the background, which is just the distribution of the velocity field in a turbulent boundary layer, that is coming from the precursor simulation, and it's not actually the wind farm simulation in this case, because you don't see, as you see, you don't see any wakes around the location of the turbine. So this is just simply the precursor simulation. All right, so let me talk about these precursor simulations, and also from these precursor simulations, we have made a lot of data available that you can use, you know, for all kinds of purposes. For instance, if you want to generate inflow data for loads analysis using, for instance, FAST, you could use, for instance, these precursor simulations as an example. So we have a 16 by 16 kilometer domain. The height is 1.5 kilometer in the precursor simulation. By the way, also in the main domain simulation, it is exactly the same layout. And I will talk today about the simulations in SP Wind. So there was about 300 million grid cells that we used. And so we have a spin up. The spin up is actually to make the turbulence realistic. And then we have what we call the precursor time, about 75 minutes of you know, real wind farm life, you could say, that are available in these simulations. Yeah, so this is actually some details about these two simulations. There's there's many different types of cases, but there's two big classes of cases, I would say. The first class is the pressure-driven boundary layer. I call it very often a half-channel flow. It is not at all an atmospheric boundary layer, but it is nevertheless, it's a simple model, it's a simpler model that nevertheless mimics somewhat the atmospheric boundary layer in case the atmospheric boundary layer is very high. And so it's much simpler to set up and to simulate than a true atmospheric boundary layer. So that's also why it is often used in large-scale simulations of wind farms. And so this is a first type of simulation that we did, this pressure-driven boundary layer. And it is actually just governed by a pressure gradient that you use to drive this boundary layer. So that leads to a certain friction velocity. And then we did different kind of roughnesses. So that leads to different types of turbulence intensity. So this pressure-driven boundary layer. So we did this simulation we did this simulation at KU Leuven and at DTU. The nice thing about this boundary layer is that you can rescale it, and that is very interesting because that enlarges the usage of the database actually. And I will show later also how that works. But essentially, because this is a very high Reynolds number flow, we know that actually the large scales in the flow, that they asymptotically scale, you know, that they become asymptotically independent of the Reynolds number. And that is true for, you know, for the scales, definitely also at the size of the turbine. So we don't actually need to worry about the Reynolds number. And so then the solution becomes scale invariant, meaning that that we can just simply rescale. So you have the database. Imagine the database gives you a hub height velocity of 9 meters per second, but you want to have a hub height velocity of 4 meters per second. And you can just simply rescale. So you rescale the database to 1 meter per second, and you multiply it with 4 to get 4 meters per second. So as a result of that, you also get a new time scale, which you can also simply figure out. So instead of 75 minutes, you get a shorter or longer time span, depending on how you do the rescaling. And there's also other ways you can rescale. You could, for instance, also rescale actually the height of the domain, but that's less useful because possibly you may end up that your turbines stick out of your domain if you do that drastically. There's another trick that you can do. You can also shift the mean velocity, and that is related to the idea of inner-outer separation in boundary layers. So in a boundary layer, in the outer layer of a boundary layer, and actually the wind farm is in the outer layer of the boundary layer, you will not, you know, the velocity deficit function will not depend on the surface roughness. And so you can actually change the surface roughness, and changing the surface roughness gives you, let's say, a velocity shift. And that's also something that you could use to pick up the database and basically change the velocity in specific ways. So the combination of both scalings allow you like quite a lot of flexibility to take the database and rescale it to a type of velocity that better matches what you are interested in. And I'll come back to this with an example later. So this is one type of simulation that we did. Then we have another type of simulation that we did, which is a conventionally neutral boundary layer. This is much more what you can have in an atmospheric boundary layer. So basically what you have is you have obviously the ground surface, and then you have a layer that is more or less neutral. It's something that can happen quite often offshore. And then you have at some point at maybe a kilometer, or depends actually, you have a capping inversion where you have a strong inversion layer, and then you have the free atmosphere, you have some kind of a free lapse rate, let's say. And this system also has Coriolis forces, and because of that, you have this kind of turning of the velocity if you go from above the boundary layer towards the turbines, and that can also lead to wind veer and things like that. And then the height of this capping inversion also depends on, the temperature jump that you have here, and these are actually external conditions that would come from a mesoscale from the weather system, let's say. So basically, in this conventional neutral boundary, we have try to set up different of these type of systems. And so this is a system that is driven by the a geostrophic balance, which is basically what happens above the boundary layer. So in this region, and then below you have obviously the friction with the Earth surface. And also here you can actually do some scaling, but now you need to take into, it's also analytically independent of the Reynolds number, but now it will depend on the Rossby number, which is related to Coriolis forces that you have here. And then you also have an non-dimensional group related to the strength of the capping inversion. But nevertheless, you can also do some rescaling. So if you rescale the velocity, then actually that implies that you change the latitudes of your simulation and also the strength of the capping inversion, but you can do it. And the shifting is also something you can do, and that actually does not make any difference with respect to latitude. So we did different kind of conventional neutral boundary layers as well in this precursor setup. So we did different strengths of the capping inversion, so 2 degrees, 4 degrees, and 8 degrees. And if you increase the strength of the capping inversion, actually the boundary layer will be lower, or can be lower, let's put it like that. So actually that's some kind of an equilibrium height. So meaning that with this strength of capping inversion, the boundary layer will not grow further due to turbulence. If you would have a 2 degree capping inversion at this height, turbulence would eat away and would push up the capping inversion to roughly this level. That's basically what it means. So this is actually, this is not the capping inversion, sorry, this is the velocity field that you get. Here you see the capping inversion. So this is actually here you see the capping inversion. This is actually the temperature jump that I was talking about. And then because of this, Coriolis system, you also get a lot of wind veer. So this is the flow angle as function of height. And you see that that can change dramatically, like up to 20 degrees in the most extreme case. Okay, so this is just an impression of one case and the amount of detail that is available. So we have a 16 by 16 kilometer domain. As you can see, you have the U, V, and W velocity, and then you can zoom in actually, and you see also in the zoom that there is still a lot of detail available, in this case on a 2.5 by 2.5 kilometer domain. So this kind of data is currently available on a shared data platform. I will come back to that later. So regarding this, how you can use this rescaling. So this is something that we're currently doing for Lillgrund. So actually the measurement campaign finished recently. And so we got the inflow data from the LiDAR measurements. And so what we now want to do is actually, we want to match the LES precursor simulations to those inflow data. So essentially what you have is you have a LiDAR measurement. So this is actually, for instance, this orange line, it's a LiDAR measurements along the range gates. And we have them for, 6 months. And so what you basically try to do is in some kind of way, you try to find an LES precursor simulation that matches in some kind of way this data, or let's say that matches the LiDAR data over these 6 months range. That's what we're trying to do. And so you're trying to find an error measure between, what we get from the LES and what we get from the LiDAR. And there's different error measures that you can come up with. You can just use, match the mean velocity profiles along the range gates. So the LiDAR is, by the way, is pointing upwards at an inclined angle. It's not vertical, but like at some angle. I think Elliot can tell you which angle precisely. And so we can either match the mean velocity profiles along this direction, or you could look at the covariance matrix and try to match those to you. And then basically we do an optimization over all possible scalings that we can use in the precursor data to see, how we could actually get a precursor data that matches somewhere the LiDAR over the measured range. And this is just an example here where you see some matches that we find either between a conventional neutral boundary layer and some LiDAR measurements. So that and this is a match between a pressure-driven boundary layer and some other LiDAR measurement. And you see very good match in kind of the velocity magnitude over the range gate. But what we see also as well is actually that if you look at the variance that actually, so for instance, you should compare red and orange, then you see that the variance of the red signal is a lot less than the variance of the orange signal. So that's because we did a certain type of optimization of trying to match these signals. So you could also include, the matching of the covariance matrix, and then you see that you can also find good matches between both signals, both the let's say the turbulence intensity at hub height here and the shape of the velocity profile. So this is something that we are currently working on. It's actually very preliminary, but once we have good matches, we are going to use those specific inflow data sets, but scales to our needs to basically do Lillgrund simulations and then compare those simulations with the measurements that also done inside the farm. Okay, so let me briefly also talk about the wind farm simulations. So these wind farm simulations are not about the Lillgrund wind farms, but they are about the reference wind farm. So the 10 megawatt turbines, okay? So in these simulations, we have aeroelastic actuator sector models. So they have like a multi-body representation of the tower and the blades, using a projection on the first 3 or first 4 modes, typically always. So for the blades, I don't know exactly anymore. I think it's about 3. And then for the tower, it's also some modes there. So I think that the blades has probably the first 2 flap-wise and then an edge-wise, and maybe also torsional. So it's actually more than 3. And then we use an actuator sector model. So we are not using an actuator line model. We actually, in a simulation of the wind, we kind of sweep the blade over a certain sector, and we kind of accumulate those forces that the field feels over that sector. And during the sweeping, actually, the blades are moving in the multi-body framework, and actually all the angles of attacks are then calculated, etc. And the idea is actually that the wind doesn't feel such fast changes. At least the wind at a larger scale only feels this accumulated effect. The reason why we do it is because we want to be able to make bigger time steps in this, very big wind farm simulations. So we tested also this actuator sector model output with reference data on the 10 megawatt wind turbine. So that's basically a combination of fast and aerodyne, I presume, or maybe bladed, I'm not sure. But we matched very well our elastic model with those models. So our elastic model integrated in this SP wind code, and actually at DTU they did the same. So there is a combination of HAWK3 and Ellipsis 3D. Okay, and then we did the wind farm, but at different rotation angles. So and there was different setups actually. So here you see the different setups from DTU and from KU Leuven. So different angles and different inflow conditions. I'm not going to go through the table; it's a bit boring. But most wind speeds here are around, between region 2 and between in the region overlap region 2.5 to 3, let's say. So for the KU Leuven runs, this is just a picture of possible outputs in terms of farm power, but there's a lot more detail available. But you see, for instance, different inflow angles here: 0, 90, 30, 90. So going back here, 90 degrees is 0 degrees is this situation, 90 degrees is this situation. So where you have the very deep wind farm, and then you have situations in between. So you see that the 90 degrees is always a lot less power, right? You see in orange the CNK8, that's the lowest boundary layer. That's a very low boundary layer. And then you have like CNK4, that's a higher boundary layer, and CNK2 is a still higher boundary layer. And these are the pressure-driven boundary layers. Everything is normalized with the first one here. That's just a way to present the results. But we then also have a lot of results on fatigue and fatigue loading. And in practice, in the database, you have basically just all the time series of basically the multi-body model that you have. So you can basically pick any point where you want to calculate, fatigue series or something like that in this model, at least. This is just an impression of the simulation and some output. It's a side view of different actually boundary layers. So the top one is a pressure-driven boundary layer. And then you have a conventional neutral boundary layer with a boundary layer height that is around 500 meters. And then you have a boundary layer height that's around 250 meters. And actually for the lowest one, you see that there's some very interesting situations happening, because the boundary layer is so low, you kind of get these very oscillatory nature of the flow here in the wind farm. And actually, if you look back at that case, that is, this case here, you see that this, the CNK8, which has a very high dimensional load, even though it has a relatively low power output. So that's basically related to that. Okay, let me finish with data accessibility. So data sets of the K11 set are available on Zenodo, and the ones for DTU, they will become available, but they are not yet available on the DTU site. And so for now, I can only refer you to the Zenodo data sets. You find here the links, but you can also simply do a search on Zenodo and TotalControl, or you can go to the TotalControl website, the EU website, where you also find links to the data sets. And so this is just what you will find there. This for the different cases. You get the reference wind farm data set. You also can look at the precursor data sets. They are separate, and there's also Python scripts that allow you to access the data sets, to make some plots, some simple plots, obviously, but also to read the data sets because they are stored in HDF5, which is some kind of a high performance, structure for storing binary data. Okay, and that is the end of this presentation. So thanks for your attention, and obviously happy to answer any questions that you may have.
Thanks, Johan. I see one question here, and that is by Fernando D'Amato from GE. Can you give an idea of the sampling rate of this data?
Yes, so the Larsen simulations are at a rate of 0.5 seconds, something like that. But the turbine data, so the multi-body simulations, there are sub-time steps in those, and so that I don't know exactly, but I think it's probably like something like 100 hertz or something. That's what I guess, roughly speaking. But you can find, obviously, I can give you the precise details if you're interested, or you can find it on the Zenodo database. So the flow at let's say at 0.2 hertz, 0.5 hertz, and the turbine model at around, I guess, 100 hertz.
Fernando, does that answer your question? Okay, maybe we can actually do it that way. Yes, good. We can do it that way, that you can switch on your camera and ask that personally. Pete Bachand or Bach.
Bachand.
Yes, Bachand. Sorry.
Oh, looks like it's using the wrong camera. Okay. Oh, I guess my camera's not going to work. Anyway, my question is, given that RANs can be much more computationally inexpensive than LES, have you ever tried or had any luck replicating some of the mean results you get from the LES using RANs?
We don't do any RANs, so it's not the thing what we do in our group so much. But I could refer you to, for instance, Paul van der Laan, who is actually very active at DTU in doing RANs. He's very good, doing very good work on that. And yes, I think you can definitely do a number of things with RANs. What you will not be able to do, obviously, is the terminal fluctuations. So RANs is a steady method, so that you would have a hard time in getting all the details of the terminal fluctuations that would, for instance, also lead to loads.
Right. Thanks.
Any more questions to this one? Or will you now all flock over to Zenodo and just play with it yourself? Feel free to. That's what it's for.
Absolutely, feel free to do that. And actually, we heard already that some people have used those data sets already. And actually, it's also a data set that has been picked up in the Farm Corners project for some referencing and benchmarking.
And if you haven't heard, then right after this one, we are going to have a workshop from the Farm Corners project where we're discussing certification and standardization and similar issues, also pertaining more to the industry rather than TotalControl, which is a bit more from the academic side.
Yeah, maybe I should also add that obviously this is a simulation data set. It is not reality. And so we are also very happy if you kind of point us to, things that we could do better or whatever, or things that do not match up with what you see in real life. So obviously that is also one of the reasons to share it, that in the end, it may also help us to improve our tools.
Okay, if that concludes it, then you might want to stop sharing, Johan. And we're going over to Ervin Bossanyi. He's, I think, principal engineer or something like that at GE. No, sorry, at DNV in Bristol. Has been around for wind energy for longer than we care to remember, and is the person who coded the wind turbine controller for the Ori Catapult Levenmouth turbine, and now is doing the experiments with that one. He's also the work package lead of work package 3. Please, Ervin.
Thank you. Yes. So can we hear me all right?
Yes.
We can hear you nicely.
Good. So see the screen?
There's something coming up on the screen, should be anytime soon.
Okay. So yeah. If at any time things seem to be going too slowly on this computer, then just give me a shout and I'll stop some calculations which are going on in the background. So yeah, this is work package 3, which, as Gunnar mentioned, is about wind turbine controller enhancements. So I'm leading the work package. There are 2 tasks in the work package. The first one is completed, and this was to do with developing some new turbine controller features and testing them using simulations. A lot of these were based actually on the Samsung 7 megawatt demonstration turbine at Levenmouth in Scotland, which is run by Ori Catapult, who are partners on the project. I've got a few results on this, the different subtasks within this, which I'll present in a moment. The second task, 3.2, is about installing some of these controller enhancements on the 7 megawatt turbine, which you see there, and testing them in the field. For that, we've installed, as you already heard, 2 LiDARs on the top of the nacelle, one facing forwards and one facing backwards. And then we've been using those LiDARs together with the turbine data to generate a flow model for the induction zone in front of the turbine. And then in terms of the actual controller tests, first of all, there have been some yaw misalignment tests running to look at the wake deflection and also the loading on the turbine during yawed operation, which is obviously directed at wake steering control on a wind farm. We've got some power reduction tests, which also is useful for axial induction control on a wind farm, but also useful for grid ancillary services if one is asked to curtail power in any way. Then we've got individual pitch control tests where the turbine already has individual pitch control, but we're testing some enhancements to that. And then we're testing LiDAR assisted control using the forward facing LiDAR to give a wind preview. Delta control tests is to do with reducing not the rated power of the turbine, but reducing power at any wind speed in order to reduce thrust, again for wind farm control, for axial induction control. And then we've got fast frequency response, which is very much for grid ancillary services, for frequency support, where you can change the power output of the turbine on a very short time scale in response to measured grid frequency. And finally, there's some work on model predictive control. So the first task was to generate a bladed model of the turbine and a reference load set. That was done early on in the project. That was then used by some of the other 3.1 tasks to develop particular controls. This is the down regulation, the reduction of rated power, and DTU did a study looking at 2 different algorithms for this. On the left is maintaining let's give us a pointer. This is keeping the rotor speed constant, changing the torque and hence the power. And this is the change in pitch angle that you get. On the right is allowing the rotor speed to decrease. That's this graph here. So as you decrease power, you also decrease rotor speed. And that can be beneficial for loads. And the point of this is to look at different load effects. We then took that algorithm from DDU. We implemented it in the real turbine controller. And I should say I didn't actually design the real turbine controller, but my colleagues at DVGL did. Well, I was part of it, I guess. We implemented this algorithm in the controller, tested it in bladed simulations. You can see the constant speed simulation here, and this is a set of simulations with a varying speed. It's important to test it in the real controller. You get all the real world issues. So this controller has a big speed exclusion zone here to prevent tower resonance. You can see here the different speed torque curves for different wind speeds. And when you allow the rotor speed to change, you hit the speed exclusion zone. So we had to make absolutely sure that that was all going to work properly. Another part of this task was to look at the virtual synchronous machine concept. And this is something that SINTEF did. This is where you change the control of the inverter to change the power output to the grid on this side in response to grid frequency. And they looked at a couple of different schemes in simulation where they simulated an onshore grid and the wind turbines doing this control. They looked at a couple of different schemes. One was where you're using the DC link capacitor to draw energy from, and the other where you actually feeding through to the turbine here, so you can use the wind turbine kinetic energy to provide power. And that is obviously a much more capable scheme because you've then got a massive flywheel here which you can make use of. So that was one task which was completed using simulations. We can't do this on the turbine, unfortunately, because we can't muck about with the inverter controls. So that was just simulations. This is another simulation only part of the task looking at active tower damping for offshore turbines. Again, a simulation study done by SINTEF. They used a very high resolution model and a top-down controller to answer some questions like, can we steer the direction of the tower oscillation to control how much fatigue is accumulated at different points around the tower circumference? And offshore, of course, you've got wind wave misalignment and all sorts of effects like that. The answer was yes, you can, but they didn't identify any particular advantage in doing that. The second question, can you control generator torque and or blade pitch to provide effective damping and rejection of ocean wave loads when the turbine is idling? And again, yes, they could, and various different strategies, you need different strategies in different situations, but that was definitely a possibility. Model predictive controls, work done at DVGL by Martin Elliot. This was a simulation study using a model predictive control in MATLAB with communications to the control DLL, running in bladed simulation. This was quite successful by closing the loop before posing the optimization problem. You really simplify some aspects, this worked very well, especially for handling the transition around rated, which is a very kind of non-linear moment on the control curve. This was developed for a 2 megawatt generic turbine and then applied directly to the Samsung 7 megawatt model without any tuning, so that worked very well. LiDAR assisted control, this will be implemented on the actual turbine. This is the scanning pattern of the upstream upwind pointing LiDAR. This shows some simulation results. So up here, you have the tower base nodding moment, and the black is with the LiDAR assisted control. So it's reducing the fatigue loading there. And the pitch action is actually smoother as well. That's the blue line. And this shows the tower base fatigue load reduction in different wind speeds we're getting from the simulation. So this is going to be tested in the coming year on this 7 megawatt. Individual pitch control. The existing machine already has 1P individual pitch control using blade root sensors. The objective here is to look at, first of all, adding 2P IPC. This is twice per revolution IPC. This can reduce more loads. So rather than reducing just the low frequency nodding and yawing moments, you can also reduce the 3P nodding and yawing moments, which are much bigger fatigue drivers actually. So that can be quite useful for reducing loads. This is the blade root moment where the 1P reduces the 1P loading and the 2P reduces the 2P loading on the rotating blades. There's more pitch activity, of course. And this shows fatigue load reductions as a function of wind speed at the blade root and tower top. The other aspect of this experiment is to use tower top sensors rather than blade root sensors. And we've shown theoretically that you can do this. And both for 1P and 2P IPC, and these sensors are likely to be cheaper and more robust than the blade root sensors. Show that it does work almost as well as the blade root sensors. Okay, so we install these LiDARs. The two LiDARs you already seen. This is the forward-facing scanning pattern. This is a scan from the rear-facing LiDAR. So these were installed on the turbine, calibrated and so on. We already talked about that. This is the wind field model for the induction zone, which has been looked at using the forward-facing LiDAR. When the wind is blowing more or less from the met mast to the turbine, the LiDAR is scanning along this, in this area here. And by looking at the SCADA data from the turbine also, you can deduce the time taken for wind speed disturbances to move from the scanning distance to the turbine or from the mast to the turbine. By looking at correlation analysis with different time lags, you can identify that advection time. And then this is a fit of those measured advection times against a model. So that's proving quite useful. Could be useful for improving LiDAR assisted control. Okay, so the field testing program is like this. So the yaw misalignment tests are nearly complete, and the controller has been upgraded to include the various new features to be tested on controller. So the down regulation algorithm from DTU, this is the rated power reduction. That's all ready to go pending some final approval. We have to get approval to run each of these tests. The delta control, this is power reduction or thrust reduction at any wind speed. That's ready and approved. Simulations have been reported. There wasn't an official deliverable on this, but we have a report on that. 2P IPC is ready and approved, so that can start. Tower top IPC is also ready and approved, but we're still waiting for a bit of hardware to connect the strain gauges to the PLC. It might have been done by now. LiDAR assisted control is ready, but still needing a final approval. So all those things will be happening, hopefully starting fairly soon in the new year. Fast frequency response, we're still preparing that algorithm to put on the actual controller, but that's in progress. The field testing has been delayed a lot due to all sorts of issues, which is what you'd expect with this sort of field test. LiDAR installation, hardware faults, strain gauges, the need for safety approvals, COVID-19 delays on site and having to wait for weather windows. That's what you expect with field tests. So we've got a good excuse for our delays. But we've got a year now to try and get all these tests running and analysed. So there we are. Your misalignment tests are going very well. This is the test matrix of different wind conditions, different yaw angles, which is filling up nicely. This was back in November. We're going on to 25 degrees yaw. This is a LiDAR scan with the rear-facing LiDAR showing the deflection of the wake. This is a particular case at 20 degrees yaw. So that's going to be very useful for comparing it against wake deflection models. The delta control, this is some example simulations showing the different thrust reductions. These are actually thrust time histories during the simulation. What we're doing here is trying to maximize the thrust reduction while minimizing the power loss by choosing appropriate pitch angles and rotor speed, torque speed schedules to change the rotor speed. And this is implemented in the actual turbine controller. And again, this speed exclusion zone is an important factor here. So this is generator speed and torque on this graph, and this is the normal trajectory that we would have here with a big exclusion zone. And then for the different delta settings, we increase the pitch angle, we change these characteristics, and we had to change the parameters which control the crossing of the speed exclusion zone in order to make sure we don't cross that zone too often or at the wrong times, and we cross it at a suitable speed and so on. So that's all ready and done. The last deliverable on the project was to be model predictive control implementation on the turbine. And the aim was to create an MPC algorithm based on the work I showed you earlier in the first part of the work package that could run on the 7 megawatt turbine PLC. But we found it's even harder than we thought it was going to be. And at the moment, we don't have a practical solution in sight. The extra computation requirements are too great, but there are also a number of practical problems, actually real life problems when you try and do this sort of thing. And at the moment, we don't think we're going to be able to progress to an actual field test, but what we will do is prepare a report in which we try to bring together the MPC that we developed earlier on, plus all the different MP solutions from the literature, and explain how these relate to the real world challenges that you have to put MPC on a wind turbine, and to try and explain what the real problems are and to fill the gap between academia and industry, which should be, I think, a very useful input into this, because model predictive control for wind turbines has been talked about for very many years. Many people have looked at it, but we're not using it, and there are some fundamental reasons why it's actually quite tricky, and I think this will help to shed light on that. So the schedule finalized the induction. So model report, it's more or less finished. Frequency response implementation soon. Prepare the report on the model predictive control. And then all the field tests that I've talked about, which are already going on now and which will be happening over the coming year until the project ends in December next year. So that's the plan. Okay, that's the end of that presentation. I haven't got a nice slide saying questions, but if you have got any, I'm happy to answer them.
I actually haven't seen any questions in the chat. You might want to check the chat. I sent some of you personal messages as well. Oh yeah, there. Mahmoud, can you just come up and ask that yourself?
I'll try. Can you hear me?
Yes.
Hi. Thanks, Ervin, for a nice presentation, like always. How does I don't know if you have found got the final results from the Samsung test that you mentioned. What so far? How does it compare against the latest test that D2 had on V52 turbine? Thank you.
For the yaw misalignment tests, the wake deflection, yeah. Yeah, no, we haven't analyzed the results of those tests yet. DTU have looked at some of the LiDAR scans to make sure that they are producing the information that we need, but it hasn't actually been analyzed yet. So we don't have an answer for you on that yet.
The analysis is in progress, and of course it's the idea to compare with our model efforts also from the Samsung turbine, as we did with the V52. So that will hopefully nicely supplement that work.
Yeah, thanks. Thanks, Gunnar. Thanks, Ervin.
I have another question then. You showed that, at least in the plot you had of the map, that the wind just coming along the coastline. How is the coastal effect influencing the measurement results? Or is there any influence at all because it's quite high above the coastline?
Right, I don't know myself. I haven't looked at that. I don't know whether Elliot or somebody could comment on that. No. I'm just going to bring up the picture there that you're talking about. This one, yeah. Yeah, I mean, it's way above the coastline. There is also a lot of buildings upstream, some way upstream. There's a village, so there's turbulence from that. Actual coastal effect, I don't know, I'm afraid.
But I guess the nice thing with this inflow direction is that we also have a met mass upstream. So to the extent that we don't have the LiDAR that can scan as far as upstream the induction zone, then you might take advantage of information from the met mass recordings. But yeah.
Yeah, the information we have, if we don't use the directional line from the met mass to the turbine, is the shear information, because we can get the inflow speed and some other information from the forward-facing LiDAR, but that's the main reason why we've needed to align the two.
Good. I see one more question. Zhufeng, can you pose that yourself?
Yeah, thanks for your presentation. I'm curious to know could you elaborate a bit on the challenges of model predictive control? What are the challenges?
What are the challenges? Yeah. non-linearities, turbulence. There's the fact that turbulence is a very strong disturbance, which is also unpredictable or very stochastic. I think to answer the question properly, I don't suppose Martin Elliot is on the call. He is the expert on this. Although I've dabbled a little bit in, not actually in model predictive control myself. He's thought a lot. Pretty useful, but I don't anticipate.
I think, to my understanding,
lost you for a moment.
Challenges is the completion capacity of the IPC. That's at least what I got from a discussion with Alan at the DTU. So to some extent, the modeling is working nicely, but the capacity, the completion capacity on the turbine controller is, as far as I understand, not sufficient to do what is needed there.
Yeah, I think the computation capacity is clearly not enough. We were looking at solutions for adding extra computation capacity to the turbine, but I think what Martin is telling me is that there are some more fundamental problems that in the real world which are going to make it even more difficult than he was hoping. But I don't want to elaborate too much on that.
Okay, I think in the interest of time, we are closing that discussion here. And if you have more questions, then Ervin is going to be available for direct interaction. And with that, thank you, Ervin. And the next speaker is Anand Natarajan from DTU Wind Energy. He's the head of section for, I don't even know your new section name. You better introduce that yourself, but he's also the work package lead for discussing loads. And that's, of course, another interesting topic for wind farm control. Please.
Yes, thanks, Gregor. So I'm heading a section called structural integrity and load assessment. So we look at loads prediction on wind farms and life prediction and fatigue, among other things. Is my presentation visible?
It is indeed.
Okay. So I lead work package 2 in TotalControl, which looks at the open loop controls for the wind farm in terms of derating and looking at the effects of derating or power curtailment on the wind farm power production, as well as the fatigue load reduction potential from derating. So here I am talking about a more subset of this, which is the surrogate models that is used for predicting the fatigue life consumption or the remaining life assessment of the wind farm turbines, as well as looking at what happens to the power production. So most of the work here would be was done by my colleague here, Nikolai Dimitrov, who could not be here, so but I will present the work. So in terms of surrogate models for wind farms, this is a fairly large topic in itself. We use the collected data from wind farms in terms of scalar measurements or any other type of measurements that is there in the wind farm, combine it with an aeroelastic simulation tools such as HOP2, along with the wake models such as dynamic wake meandering, and then use this combination of simulation and measured conditions to predict both the power capture as well as the loads on all turbines in the wind farms for all conditions. So as a function of the ambient conditions in terms of different mean wind speeds, different ambient turbulence, and wind directions, to come up with look at the fatigue that each wind turbine is suffering, as well as the power production coming out from each wind turbine. This is done here primarily using neural networks. We also have surrogate models based on other methods, such as, for example, polynomial chaos expansions, where you can assume statistical functions which look at combining polynomials with different types of stochastic distributions and having a summation series about it. But neural networks have shown the most promise in these type of approaches, where we have at least 3 layers of neural networks with the input layer, a hidden layer, and an output layer, and looking at feeding in the data that we measure in terms of wind conditions and the potential SCADA measurements as input, and training the neural network based on the outputs from aeroelastic simulations in terms of both the loads and power productions. This is usually a highly involved process, so it takes a lot of simulations. But once the simulations are there, then the output from the neural networks can be used for new measurements. Wherein on Lillgrund we have applied it to several years of measurements, wherein we can say what is the power capture or the loads from each wind turbine as a function of wind direction or of wind speed, and thereby look at the most heavily loaded turbines for assessing the remaining life of these turbines. Here we see what is the type of inputs that the neural network can have. Primarily, we are looking at the wind inputs in terms of the wind turbulence, the wind speed, the wind shear, the wind direction. Then we can also take into control inputs in terms of derating certain turbines, in terms of reducing the set points of speed and pitch of the turbines, as well as the position of the turbine within the wind farm, in order to predict both the power and the loads on all the downstream turbines. As I mentioned, there's a large amount of simulations done. So this is the overview of the Lillgrund wind turbine with 48 turbines. They're Siemens 2.3 megawatt turbines. We look at least 1 hour load simulations for each of these wind turbines with wake effects from at least 5 upstream turbines. And then overall, this if you sweep the wind direction and the wind turbulence and all mean wind speeds, it comes up to more than 100,000 simulations that are done in order to train this surrogate model. But having trained it, then the representation of the full wind farm becomes quite obvious. For example, here what you see is the power output of the whole wind farm as a function of the wind direction for each different wind speeds, where it's obvious that in certain directions there is a very predominant wake effect. And the same thing can then be done in terms of the loads. So if you look at the damage equivalent loads at the blade root, again, the same predominant directions for where the wake effects are manifesting can be identified. While this is an example of the output, one can also go into each wind turbine to see what is the tower base or main shaft or blade root loads, and then see the effect of for example, derating or curtailment of the upstream turbines in seeing how much of these loads can actually be reduced to improve lifetime, and also consequently what is the penalty on power production that is there if you do derate these turbines. Sometimes by derating, we can also get an increase in the power production, which is due to the reduced wake effects. This also allows that we are able to combine both the measured information as well as the simulation-based information. So you see into the surrogate model. So what you see here is at one mean wind speed, the left-hand graph shows the measured electrical power contour map on Lillgrund. And then if you take the neural network model based on the measurement or based on simulations, we can still get the same output comparability to the measured case in terms of the predictability of the neural network. So this could you can use either the data from the measurements as input, or it could be simulations or a combination of both, and we get about the same fidelity of output from the neural network. Another useful way is to look at the damage prediction over a continuous period. So here there's a movie running. I hope you can see the movie, wherein what you see on the left is a continuous power production over several days, and then you see on the middle graph that the damage equivalent load at the blade root, where you can see that some of the turbines at the back of the wind farm, when the wind is coming from the southwest, are more orange color or having more damage. And on the far right, you get the accumulated damage as it builds up over the right of the wind farm. So this looks at a full simulation of the wind farm fatigue and power output on a continuous basis. And so if you're recording SCADA measurements on the power on a continuous basis, then one could just use that as an input to the neural network to continuously track the damage over the wind farm and see which turbines are getting more and more damaged, to look at as an input for potentially for inspections, or maybe as an input to the wind farm control to say if we can lower the load on these turbines. And I've been mentioning the word derating a lot, so that is also something that can be used in this context. So on the figure on the left, it's the same figure that we saw from a couple of slides back, that is a power production at 9 meters per second without any derating, and in the figure on the right, we derate the second row of Lillgrund turbines by about 20%, and then see the effect on the downstream turbines. And in this case, even though you have derated the second rows to a significant amount, we still get about an overall 4% increase in the energy capture at this wind speed. So the denseness of the wind farm allows that we can derate and still get an increase in the energy capture. And of course, this derating also allows you to recover some of the fatigue damage that has been consumed in these turbines. Another useful tool for the surrogate model is to be able to predict wake turbulence. So as from the measurements, we normally use the Nessel anemometer, which of course is useful for the mean wind speed, but not so useful for measuring turbulence. But then we could use the other SCADA signals to correct for the turbulence, so that we can have a better estimate of the turbulence seen by each wind turbine within the wind farm. This can also be done by a similar neural network, but here we just use the measured signals for training this neural network, and we can compare that with the out from what is correspondingly used in aeroelastic simulations, and combine the two to get a reasonable estimate of the measured turbulence for each wind turbine position. So this doesn't need to use wake model. So if you're able to get this measured turbulence, then the added advantage is that then that could be used for loads assessment using pure SCADA signals without the need for a wake model. So here you see a pictorial view on the left of the turbulence at one of the wind turbines in Lillgrund, along with the measured turbulence from the Nessel anemometer. So you get a similar variation from the neural network, except that the variation is lower, and the mean turbulence over mean wind speeds is more or less the same. This also allows you to capture the turbulence intensity profile, which you see on the right. And then if these wind turbines are certified for a certain IEC class, for example, class 1A or class 1B, then one can use this to monitor the turbulence that each wind turbine is suffering, and then look at derating the upstream turbines if the turbulence level of a certain turbine is reaching a certain threshold, which the wind farm owner could look at as being detrimental. So this looks, so as you can see here, we can base the derating based on the turbulence, and on a lookup table to see at what turbulence level do you start changing the rotor seat suspect points or generator torque to start derating the upstream turbines, and consequently start lowering the wake turbulence of the downstream turbines. And that's something that we're doing right now. So I don't have results to present on the wind turbulence aspect, but but overall, that this is something that we're working with more in terms of validating. So as was mentioned in some of the earlier presentations, we are now looking at doing some of these experiments on Lillgrund, where the deratings are being implemented in work package 2 on some of the turbines, where we measure on the downstream turbines both the loads and the power, and then using that we try to validate our prognosis on how beneficial is these derating to both the power production and the loads prediction for these turbines, and that allows for a real-time tracking of turbine performance and life estimation on a real-time basis, because it allows you to feed the SCADA signals into a neural network and see these quantities as they vary over the life of the farm. Okay, thank you. That was, I think, my last slide. So if there's, I can't see if there is any questions, but please speak up.
Hello, this is Andreas Maniok speaking, DNVGL. Hello, Anand.
Hi, Andreas.
Very interesting, this surrogate model and the implementation of neural networks. So I wonder how much effort you have taken in advance to train those neural networks to estimate then the fatigue. If the networks, of course, then running, they get very quick fatigue results based on their digital twin, but of course you need to train such a system advance.
Yes, so so in this slide, as I mentioned, for the Lillgrund here, I mean, there was a substantial amount of training done. So you can see that overall about 180,000 simulations were run, and wow. These are 1 hour simulations. So it's run on a computing cluster. So that takes into account a lot of wind variations in terms of the free stream turbulence, the derating of some of these turbines, as well as the different wind directions in small direction winds. So that is a lot of let's say a lot of simulations run. One could reduce that set based on what is the prime reasoning for use of this neural networks. If you feel that some of these, so you could perhaps, for example, divide this wind farm into a few sectors, and you might want to say that you're only interested in the wind turbines in one of these sectors, then maybe you could reduce the number of simulations. But here we looked at all turbines with the same level of fidelity, in which case you end up with a large number of simulations needed to train the neural network.
And maybe another question right after. Do you think it would be possible to use a reference wind turbine neural network to apply on different turbine types? So 3-bladed horizontal axis turbines of different size, for example.
Yeah, that's an interesting question. We have tried that on a different project. So we had a project that completed last year called LifeWind, where we tried that. So we had 3 different generic turbines, which were I think it was close to 1 megawatt, a 1.5 megawatt, and a 2.5 megawatt, and they were on land. They were not offshore, and we didn't have the manufacturer's aeroelastic model for any of them. And then we used a generic turbine and then measured SCADA signals to the output of the aeroelastic simulations with these measured turbines. And so in terms of I think average life capture, that is possible. So it gives a good indication of potential remaining life in some of these wind farms if you have good quality SCADA measurements available from all these wind farms. So it shows promise, though I think it needs more validation because we used only some specific turbines, and whether it can be generalized to any turbine, I do not know. But I think if you have high frequency SCADA measurements, which you can match with some of the aeroelastic simulations of the generic turbines, then it shows promise.
Very interesting. Thank you very much.
Thank you.
Thanks. There's one more question by Filippo Campagnolo. Are these DWM simulations data available outside the consortium?
Well, for this particular turbine, since it is since these are from the manufacturer's own turbine, I'm not sure that we are allowed to share these simulations outside of the consortium. But we do, I think, have more generic turbine simulations from the DTU 10 megawatt, which in principle, I guess, could also be shared.
Thanks.
I think there's one more question.
Yeah, that was it.
Yeah. Okay.
And with that, I think in the interest of time, in the interest of having a break before the Farm Corners workshop afterwards, thank you, Anand. And I'll get the last speaker on the screen, Karl Merz. He's from Syntef, and he's the work package lead of work package 4, closed loop control. Then again, I don't see Karl actually in the list of participants, which in turn okay, his presentation would have been about a linear state observer for the design of wind power plant control algorithms. And unfortunately, that is a thing that we have to show in the last newsletter that we sent out. The newsletter points to a deliverable, which then in turn is a relatively strong strong description of the whole thing. While we're having that, are there any questions regarding the entire project? And please remember to.
I can see that Katrin is trying to catch Karl, so see what that results in.
Do we have any general questions to the project? Or ideas what we should do? The project is running another year, so the entirety of next year, and we are still running some tests on both the test facilities and, of course, are now heavily into the comparison of the simulation results and the controller development in the last year. Okay, so we seem to have lost Karl, but
for some reason he doesn't seem to be available.
Yeah. Interestingly, he was the first one to answer to my question whether he would have time, but never mind. Happens.
He was just not aware of it. Or I'm his close colleague. I just told him, and well, he just seemed surprised.
Happens. Anyway, yeah, if you have any ideas for what we should do next year, speak up now. We still have a few minutes, and then we'd have half an hour break. And then we would get into the workshop of Farm Corners. Which is about, I would say, more industry relevant topic on how do we actually certify this.
I could ask a question. So the wind turbine and the wind farm controllers that are being developed, is that something that will be made public for commercial use?
Actually, it's Karl Merz who's the work package lead on that one. But yeah, we promised to have a wind farm control toolbox openly available afterwards. So some of them at least are going to be open source. And I know that he is quite a proponent of open source So I'm pretty sure that his models are going to be open sourced.
All models are, yes, they are already. They are on GitHub. Just lacking user support at the moment.
Yeah.
Maybe something to put in the next newsletter with links to those.
Yeah, I think that's also something for the final webinar, and maybe also a training session. We also promised some training sessions where we could, and that would be in the second half of next year, where we could actually have some training sessions on those control models. More like a hands-on workshop with exercises. Okay, but if there's no more questions, then I'll see you in half an hour on the Farm Corners workshop. Same place, same stream.
And thanks to everybody for participating.
Thank you, Gregor. Be invited to join afterwards.